We are now at the point in the course where we are done looking at linear relations and we are going to begin looking at quadratic relations. This is what the bulk of the grade 10 course is focused on and what you will continue to look at next year as part of your grade 11 course. So we know that with linear relations, we had two different forms of our equation. We had y equals mx plus b, which is our slope-intercept form, and we also had our standard form, which was ax plus by equals c. With quadratics, we will have three different forms of the equation, which we will look at a little bit later in one of today's videos, and we will investigate each of those three forms further throughout this unit and the second quadratics unit. First, we are going to look at what a quadratic relation is and talk about some of the key features, and then we will graph a few examples of them just to kind of see what they can look like in various forms. So when we graph a quadratic equation, it forms a shape that is called a parabola. So that's the shape that you see here on this diagram. Okay, it kind of looks like a U shape. So this is called a parabola. We can also refer to it as a curve. I know it's kind of a funny word to say. It's not parabola, it's a parabola. It's, like I said, opens up here in this case, and it looks kind of like the letter U, and if we were to zoom out on the graph, it would continue opening up infinitely in this direction as well as in this direction. So we are going to look at some of the key points and key features of a parabola, both in this diagram and then we'll talk about in general as well. So you will see labeled on the diagram here, we have an x-intercept labeled here, which we are familiar with. We looked at x-intercepts with lines, not so much this year, but you would have looked at them last year in grade 9. We have a y-intercept, which we definitely looked at just a few lessons ago with linear relations. We have another x-intercept over here. Okay, so this curve is crossing the x-axis twice. And we also have a vertex down here. So I am going to go through kind of the key features of a parabola, of what a quadratic curve looks like, and then we will look at some specific examples. So the direction of opening. In this case, in the diagram, the parabola is opening up. Okay, so it, obviously you can see it there, looks like a U shape. And like I mentioned, if you continued in either direction on the x-axis, it would increase forever. A parabola can also open down. Okay, so it could look like this, kind of like an umbrella shape or a hill shape, okay, where it has a high point and then in either direction on the x-axis, it would continue to open down infinitely. So those are our two options for direction of opening, either up or down. It will never open sideways. That would not be a quadratic relation. Okay, so you only have to worry about opening up, a U shape, or opening down, a hill shape. The vertex. If we look at the diagram, we can see that the vertex is right here. And you may or may not notice that in this diagram, that is the lowest point on the curve. Okay, so because this parabola is opening up, the vertex is the very bottom point here. It's where, if you're looking at what the direction is, if you're moving along the x-axis, we have the curve decreasing all the way down. We hit the vertex and then it starts increasing and it will continue to increase forever. So the vertex is either the lowest point, or if your direction of opening is down, then it would be the highest point on the curve. Okay, and like I said, you can think of it as the point where the curve changes directions. Okay, so your vertex will always either be the lowest point if the curve is opening up, or the highest point if the curve is opening down. Now the next two key features are related to the vertex. So the vertex would obviously be a coordinate, right? Because it's a point, it would be like an x, y coordinate. The equation of the axis of symmetry is related to the x value of the vertex. So again, if we look at the diagram here, you may notice that the parabola is pretty symmetrical. Okay, if we were to cut it in half, like this, it looks mirrored or the same on both sides, right? So if I were to draw a line that cuts through the middle of the curve like this, move that over a bit so it's more in the center, that's pretty good. The curve, like I said, is symmetrical on either side. So if you think back to elementary school, you may or may not have used those red kind of like translucent rectangular pieces of plastic that you would sit on top of a paper graph and you would look and see what a line or a shape or something would look like if it was reflected over a specific line. So in this case, if we were to pretend that that pink line that I drew is that red reflecting tool, the curve is reflected across that line. Okay, so the equation of the axis of symmetry cuts the parabola directly in half. The parabola is symmetrical on both sides of that line. And if we were to write an equation for it, because it's a vertical line, it would look something like x equals and then just a number. Okay, so we know that any vertical line, if we're making the equation of it, it doesn't have a slope. Its slope is undefined because the rise is just infinite and there's no run. So the slope is undefined, so our equation would just be x equals and then whatever the x coordinate is that the line cuts through. Okay, so on my diagram, I don't have any numbers on my axes, but if I look at my x-axis, maybe we can say that like this line here is, I don't know, let's say 10. So then the pink line is just a little bit less than halfway. So maybe we would say this is like 4. So we could say x equals 4 would be the equation for the axis of symmetry. And that number there, 4, would be the same as the x coordinate of my vertex. Okay, so any parabola, whether it opens up or down, will always have an axis of symmetry, and it will always be symmetrical if you cut right through the vertex. So that number is related to the x value of the vertex. The maximum or minimum value is related to the y value of the vertex. Okay, so you may think, okay, well, didn't we already talk about the max or min, which we kind of did within the vertex, but this is just specifically relating to the y value. Okay, so the max or min value is just the y coordinate of the vertex. And it's obviously either the highest oops, highest or the lowest point on the curve. I guess actually instead of saying point, point is more the vertex. It's the highest or lowest value that the curve will reach. Okay, so again, if we look at our diagram, we don't have any numbers on the axis, but we can see that this is my y-axis, and so this here is obviously the negative y values, okay, because it's below the x-axis. So let's say that this line here maybe is like -5, so this would be maybe like -7. So we could say that this parabola has a minimum value of -7. Okay, we don't need to state the x coordinate because it's not a point, it's just the max or min value, the y value that the curve will reach. Okay, so those three, the vertex, equation of axis of symmetry, and the max or min value are related in the sense that you can get the information. If you know the vertex, you can easily tell the equation of the axis of symmetry as well as the max or min value. Now the y-intercept, again, you are familiar with this from working with linear relations. On this specific diagram, this is where the y-intercept is, and this is the point where the curve crosses the y-axis. We know with linear relations there was always one y-intercept. With parabolas, there is also always one y-intercept. Okay, so it always has one. Okay, it doesn't matter if it's opening up or down, regardless of what the parabola looks like, because the x values continue infinitely in either direction. At some point, eventually, it will always cross the y-axis. We also have x-intercepts, which we can call zeros or roots as well. So all three of those names are kind of interchangeable. So you may hear me call them different things at different times. It means the same thing. Okay, so the x-intercept, the roots, or the zeros, those are all the same thing. So on the diagram here, you can see that we have two of them, right? So the parabola is decreasing. Right here, it crosses the x-axis. It continues to decrease, hits that vertex, and then is increasing, crosses the x-axis again, and then will continue to increase infinitely. So just the definition first is going to be either the point or points where the curve crosses the x-axis. And in this case, we have three options for what this can look like. Okay, so in the diagram, we see that there was two x-intercepts, and this is the most common thing that we will see. Okay, so let's say the parabola is opening down. It could look like this, and you would have one x-intercept here, one x-intercept here. Okay, or if it's similar to the diagram where it's opening up, then you could have like this. Okay, so one here, one here. So that's the most common option, is that there will be two x-intercepts. Okay, because the curve is switching directions, then it is usually going to cross the x-axis in two spots. Sometimes there is only one x-intercept, and the way that this would happen would be is if the curve has its vertex directly on the x-axis. Okay, so let's say this is the vertex. That would also be the only spot where the curve would touch the x-axis. So it would only have one x-intercept. This could also happen when the curve is opening up. Let's say it's like this. Then that would be your only x-intercept. Okay, so in some cases, there's just one x-intercept. And we can also have a third case. If you think about what the parabola looks like, you can maybe guess what this is going to be. This would be if we have no x-intercepts. Okay, so there's two ways that this could happen. So the first way is either if your curve is opening down and the vertex is below the x-axis, so like this. This will never cross the x-axis because its highest point is negative. It's below the x-axis and it's opening down infinitely, so that's never going to cross. You also could have a curve that opens up and has a vertex above the y-axis like this, and that would never cross the x-axis either. Okay, so this would have no x-intercepts. All right, so it's important just to know that those are our three options. Like I said, most commonly there will be two x-intercepts. However, occasionally there will be only one or none, and we will, throughout the course of this unit, look at some examples of actual numerical equations where we would see all three of these cases. Okay, so those are the key points and the key features of a parabola, and then we are going to look at some specific examples with actual numbers in the equation to see what different parabolas might look like based on what pieces of the equation they have. The first quadratic relation we are going to look at is the most basic one. It's what we call the parent function. Okay, so this is the most simple of the parabolas that you can get, and the equation for it is here, y equals x squared. So some important things to note, when we are looking at quadratic functions, they are what we call a degree 2 function, meaning that there always needs to be an x variable with the exponent of 2 in your equation. Okay, so you may recall that with linear relations, y equals x was the most basic line we could have. It was the parent function, and it crossed both the x and the y-axis at 0, 0 through the origin and had a slope of 1. Okay, so similarly, this is the parent function for a quadratic relation. There's nothing extra added to it. It's just y equals x squared, and we know that squared means that it's being multiplied by itself. So this is y is equal to x times x. Okay, so parent function, we're going to look at what this looks like, and then we will look at a few more examples of how the curve can change based on some changes to the equation. So first, we're going to look at a table of values, and we are going to complete the table of values based on our equation. So I'm going to look at x values from -2 to 2, and I'm going to calculate what the y value would be for each of those. I'll just kind of show my work off to the side here so you can see what's happening. So if my x value is -2, my y value is always going to be x squared. So in this case, I would have -2 squared. We talked about this when we were calculating distance with linear relations and analytic geometry. You need to make sure that you are aware that when you're squaring a negative number, when you're multiplying it by itself, the answer will always be positive. Okay, your calculator is not as smart as you are, and if you type in just -2 squared, it will likely tell you -4 because it doesn't understand BEDMAS. You need to either put brackets in when you're typing this. Okay, so exactly how I have it written, bracket -2, bracket to the power of 2. Or if you just think, okay, if I'm multiplying -2 times -2, a negative times a negative will always be a positive. So it's going to give me +4. Okay, then for the next one, -1, when x is -1, that's going to be -1 squared. Okay, which again, I'm not going to write this for every single one, is -1 times -1 gives us +1. And we're going to keep doing that. So then when x is 0, 0 squared is 0 times 0, which is just 0. When x is 1, y is going to be 1 times 1, which is just 1. And when x is 2, y is 2 squared, so 2 times 2, which is 4. Okay, so from the table of values, you might notice that there's a pattern happening here. So 0, 0 is this point here, and then we have 1 on either side of that, and then 4 on either side of that. And if we were to look at our table of values, let's say I extended it on both sides and I had -3 and +3, then the y value we can assume would be the same for -3 and 3. Okay, so we recall that I mentioned a parabola is always symmetrical, and it's symmetrical about the axis of symmetry, which goes through the vertex. So in this case, this would be what our vertex is, 0, 0, and so the curve would be symmetrical on either side of that. Okay, so I'm going to graph what the curve would look like, and then we will write out what the key features are. So if I have my x-axis here, y-axis kind of in the middle there, I'm going to plot what this would look like. Okay, I'm not going to write my numbers on the curve just because it'll be too crowded, but I have -2, 4, which is here. I've got -1, 1, which is here. 0, 0, 1, 1, and +2, +4. Okay, so this is what this would look like, and if I were to connect my dots here, it would look something like this. I have the benefit of my iPad kind of correcting this for me to make it more exact. It's okay if when you're drawing this, if yours is not perfect. It's pretty difficult to draw a freehand curve and have it look nice. And then we would put an arrow on both sides here to show that this would continue infinitely upward in either direction. Okay, so that's what y equals x squared would look like. If you are unsure of how to graph it yourself, you can use Desmos. If you haven't used it before, Desmos.com has a graphing calculator. You can just type the equation in. It works for lines, works for curves. It's pretty simple and straightforward to use. You can either go on the website or download the app on your phone. So if you hear me reference that, that's what I'm talking about. And it's a quick way to look at the graph of any type of equation, so you don't have to draw it by hand. So if we are looking at this specific graph, we want to determine the key features of it. So the first one, the vertex, I showed you in the table of values where it is, but we can also see on the actual graph that this right here is my vertex, okay? The graph is decreasing, it hits this low point, and then it's increasing. So this point right here, 0, 0, is my vertex. Okay, right at the origin. The axis of symmetry is the line that cuts through the vertex vertically. Okay, it cuts the parabola in half. So in this case, it's actually the same as the y-axis. If I were to draw this here, it's kind of hard to see because it's right on the y-axis, but it would be when x is equal to 0. Okay, so if you recall what I mentioned earlier when I was describing the key features, the equation of the axis of symmetry is always given by x equals and then a number, and it's going to be whatever the x value of the vertex is. So in this case, x equals 0. Okay, and that means that the parabola is symmetrical across that line at x equals 0. The y-intercept is where the curve crosses the y-axis, which is at 0, 0. The x-intercept, in this case, there's only one. Okay, so I mentioned in some cases it's only one. And because the vertex is sitting directly on the x-axis, there's only one x-intercept, and it's also at 0, 0. Okay, lots of repetition going on here. We're using that point many times. The max or min value, again, is related to the vertex, so that's either the highest point or the lowest point of the curve. In this case, because it's opening up, the lowest point is the y value of the vertex, which is 0. So I'm going to say it has a minimum of 0. Okay, if we looked on either side, the y values will always be bigger than that, so that's the lowest possible point. And the direction of opening, we can see from looking at it, is clearly up. Okay, so because this is the parent function, you'll notice most of the things, the vertex, the y-intercept, the x-intercept, are all the same point, 0, 0. If you think about with a line, the parent function, like I said, goes through 0, 0 and has a slope of 1. And then we look at the different transformations of it. Okay, so changing the slope to either be negative or positive, it can be a whole number, it can be a fraction, and then we shift up or down based on what the y-intercept is. So similarly, we will look at things like that with quadratic functions. In this video, I'm just going to show you what it looks like graphed, but we will take a look at how we can identify those transformations from the actual equation later on. Okay, so that's the most basic parabola you can get, and everything else we graph is kind of that parent function, but transformed. Okay, so if I look at my next equation, this has a little bit more going on here. So my equation is y equals negative x squared plus 4x plus 5. Okay, so there's actually quite a bit more going on here. We know it's a parabola because I have an x variable with a power of 2 on it. You'll notice here I also have just an x with a power of 1, right? It's not written there, but that's what the power of it would be. And I just have a constant at the end, plus 5. Okay, so we're going to take a look at what this would look like if we graph it. In this case, my x values that I have from my table of values are going from 0 to 4, okay, and then I'm going to figure out what my y values are. Now, this has a little bit more going on mathematically to calculate, so you need to be careful when you are entering this in to your calculator so that you get the right solution. Okay, so because I have this here, negative x squared, what that means is following BEDMAS, you're going to square the number first, okay, so to the power of 2, and then what's happening here is you're multiplying it by negative 1. Okay, so if there were a bracket around this, then it would be the negative of whatever your x value is squared, which would give you a positive answer, but it's not. So this is x squared, positive answer, times negative 1, negative answer. Okay, so for the first one here, if x is 0, we would have negative, I'm going to show it like this, 0 squared plus 4 times 0 plus 5. Okay, so 0 squared is 0 times negative 1 is still 0. 4 times 0 is 0 plus 5. This is going to be 5. Okay, the next one I'm going to have when x is 1, so this would be negative 1 squared plus 4 times 1 plus 5. Okay, so 1 squared is 1 times negative 1 is negative 1 plus 4 gives me 3 plus 5 gives me 8. Okay, so I don't have a ton of room to show you the full work there, but maybe I'll just show it over here and then erase it. So if I were to go through and evaluate that, I would have negative 1 plus 4 plus 5, okay, which is just negative 1 plus 4 plus 5, which is where I got my 8 from. Okay, so then now I'm going to do the same thing when x is equal to 2, so I'll have negative times 2 squared plus 4 times 2 plus 5. Okay, so if I just show this over here again so you can see a little bit better what I'm doing. So 2 squared is 4 times negative 1 is negative 4 plus 4 times 2 is 8 plus 5. Okay, so negative 4 plus 8 is 4 plus 5 gives me 9. We'll do the same thing again for 2 more values. So for 3, we'll have negative 3 squared plus 4 times 3 plus 5. Okay, so again over here, 3 squared is 9, and then I'm making it negative. Plus 4 times 3 is 12, plus 5. So negative 9 plus 12 is positive 3, plus 5 is 8. And then for the last one, 4, I'd have negative 4 squared plus 4 times 4 plus 5. Okay, so again, I'll kind of show what I'm doing over here. So 4 squared is 16, but we're making it negative. Plus 4 times 4 is 16 plus 5. So negative 16 plus 16 is just 0 plus 5 gives me 5. Okay, and you will notice by looking at the table of values here, even though my x values are different than what they were in the first equation that I looked at, my y values are going 5, 8, 9, 8, 5. Okay, so we see that symmetry again, where this we can assume is going to be the vertex because I have 8 on both sides and then 5. So we can see that symmetry in the table of values. And we're going to graph it to check and see what it looks like. Okay, so I'm going to put my x-axis. I might actually just do this. I'll have y-axis here. And I'm going to have my x-axis all the way at the bottom just because I don't need to have none of my values are going below 0. Okay, so this is what this would look like. I'm just going to actually extend this a little bit here. Okay, so this is y, this is x, and if I graph this, I have a point at 0, 5. So 1, 2, 3, 4, that's here. Then 1 and 8 is here. 2 and 9 would be up here. 3 and 8. And then 4 and 5 is like this. Okay, so if I were to connect those, then it would look like this. Again, I have the benefit of my iPad helping me make this as perfect as it can be. It's still not quite exact, but that's okay. Close enough. Okay, so we can see that this graph is actually opening down. Okay, and my vertex is up here. That's the highest point. So from that graph, I can identify some of the key features. So like I said, the vertex is that highest point there, and that is at 2, 9. My axis of symmetry again relates to the x value of the vertex. So if I were to cut the parabola in half, the line would be here. Okay, and that would be at x equals 2. My y-intercept I can see over here is where it crosses the y-axis, which is at 0, 5. Okay, now in this case, oops, I didn't actually continue this on forever. So let me, if I go down here, this is maybe going to be approximate, like this, like that. Okay, so my graph is probably not very good because I didn't leave enough room or extend it far enough in either direction to have my x-intercepts visible, but we can see that it will cross into spots. So we've got one of them is at -1, 0. Okay, that one is pretty, is a little bit easier to see. And the other one would be, maybe actually I think I drew it in a little bit of a weird spot, but it would be at 5, 0. Again, you can graph this on Desmos just to double check, but this would actually be like here is how it would look when we extend it. Okay, so there are 2 of them, and that's what their values would be. The max or min value, in this case, it's going to have a max value because it's opening down. And again, the max value is the y coordinate of the vertex, which we said is 9. Okay, so that's the highest value that the curve will reach, and then it's decreasing in either direction, so it's never going to get higher than 9. And the direction of opening, we can see, is down. Okay, so that's another example. Obviously, it looks quite different from the graph of our parent function, right? This one was right at 0, 0. It was opening up, and all of our key features were pretty much the same. They were all 0. Whereas this one is opening down. The vertex is way up here. I've got a different y-intercept. I have 2 x-intercepts. Okay, so maybe you can look at the equation that I have here and make some sort of assumption about how we got to this. But again, we will talk more about that in further lessons. Okay, we are going to look at a couple more examples of some different equations. I will say that this equation, so we had the parent function. This equation here, equation 2, this is what we call standard form. Okay, so I mentioned that there's 3 forms of equations for parabolas. This is one of them, called standard form. This next one that we are looking at, this is called vertex form, which we will explore more today. Okay, so my equation is y equals x minus 2 squared minus 6. Okay, so again, we are going to complete the table of values. My x values are going from 0 to 4 again. And we're paying attention to the equation because, again, we need to follow order of operations, BEDMAS. So we have x subtract 2 within the bracket, so we need to do that first. Then square, then subtract 6. Okay, so when x is equal to 0, what we are going to do is we will have 0 subtract 2 squared, then subtract 6. So again, I will just show my math up above here and then erase it for each one. So 0 subtract 2 is -2, and that is squared, minus 6. Okay, again, if you type this into your calculator without brackets, it's going to tell you this is -4, but it's not. We know that -2 times -2 is +4, and then we're subtracting 6. So that will give us -2. Then we're going to keep doing the same thing. So when x is 1, we will have 1 +1 minus 2 in the brackets. Square it, subtract 6. Okay, so then here we would have, so 1 subtract 2 is -1. We're going to square it, then subtract 6. So -1 squared is -1 times -1, which is +1. Subtract 6 is going to give me -5. When x is 2, I'm going to have 2, subtract 2 in the bracket, square, and then I'm subtracting 6. Okay, so if I show a little bit further up here, 2 subtract 2 is 0. Okay, we know 0 squared, 0 times 0 is going to give us 0, and then we're subtracting 6, which gives us -6. When x is 3, we're doing 3 minus 2 squared minus 6. Okay, when these ones are less likely now for you to make a mistake because 3 subtract 2 is just +1, and if you type 1 squared in your calculator, it's going to tell you it's +1. Minus 6 is going to give us -5. Okay, so we can see that symmetry happening again. You can maybe take a guess at what the y value is going to be when x is equal to 4. I will calculate it as well. So if we do 4 minus 2 squared minus 6, we know 4 minus 2 is +2. Okay, 2 squared is 4, minus 6 gives us -2. Okay, so again, we can see that symmetry happening. We've got this point here. This is kind of the odd one out. Then we have -5 on both sides, and then -2. So if I graph this, in this case, it's going to, all of my values are below the x-axis. So I'm going to put my y-axis here. My x-axis I will put like this, just so we can see where it crosses. I'll make sure to extend this a bit better this time. So this is y and x, and then I'm going to plot my points. Okay, so my first one is at 0, -2, so that would be here. Then 1, -5 is here. 2, -6 is here. 3, -5, and 4, -2. And if I were to do this, oh, okay. Draw my base here, and then I'm going to use this to kind of correct this a bit better. The correct points here. And it's kind of hard to get everything perfect, especially when you're doing it freehand. Again, I have the benefit of my iPad helping me make this a bit more exact. It's still kind of having a hard time getting right where I want it to be, but close enough. Okay, so then I would have this, and then I'm going to extend on either side here. So the vertex is going to be that lowest point there, which is 2, -6. You might notice I said this equation is called vertex form. Maybe look at the numbers there. I'm sorry, this is 2, -6. And see, what do you notice about the numbers compared to what my vertex is? The axis of symmetry, again, is going to cut through the middle of the curve here, through my x-axis, through my vertex. So that's going to be x equals 2, right? That's related to the x value of the x coordinate of the vertex. My y-intercept, I can see here, is where it's crossing the y-axis, which is at -2. So So the point is 0, -2. My x-intercepts, there are 2 of them, and in this case they're not super exact, so we'll say this is maybe like -0.5, and this is 1, 2, 3, 4, maybe like 4.5. Okay, it's not crossing directly through a nice point, so we will just approximate them there. The maximum value, again, this is the y value of my vertex, so this is a minimum value of -6, right? It's the lowest possible point, or lowest possible y value that the curve is going to reach, and it is opening up. Okay, so those are 3 different examples of different parabolas, how we can plot them based on their table of values. Once we plot them, then we can tell those key features. And the last example here, we're just going to look at one that is already plotted for us and how we can identify the key features. Okay, so if I look at this curve here, it's already plotted out for me. I don't know the equation, I don't know the table of values, but that's fine. I can still tell what all of my key features and key points are. So the direction of opening is obviously down, right? It looks like a hill. It's extending down forever, so it's opening down. My axis of symmetry would be if I cut right through the middle. So you can see here that gray point kind of labels where the vertex is, which we will determine in a moment. But if I were to draw my axis of symmetry, it's going to cut through that vertex. My line's not perfectly in the center, but that's okay. We can see that that is when x is -1. Okay, so x equals -1 will be the equation of the axis of symmetry. The max or min value, it's going to be a max value, right? Because it's opening down, and we can see that there's a high point on the curve. And that is when, if this is going up by, oh, it's not going up by 1, just a minute. Okay, so this is going up like this is 1, then 2, 3, 4. I have a few extra lines here, so I want to make sure I get this number correct. This is 11, 12. This would be 13. Okay, so my max or min value would be 12.5. Okay, if I give you questions like this to look at, I will try to have it so that your lines are all just going up by 1. Okay, so that you don't make the mistake there. I almost said that 13 was the max, but it's actually 12.5. So the coordinates of my vertex then, where this gray point is labeled, are going to be -1, 12.5. Okay, so the x coordinate is the same as the axis of symmetry value, and the y coordinate is the same as our max value. The y-intercept we can see is right here, so this is at 0, 12. And then my x-intercepts, I can write the coordinates as well, so we see there's 2 of them, one here and one here. And based on what this is, I think this is -3, 0, and +2, 0. Okay, so this one we didn't have to do any calculating with the table of values or any plotting ourselves. We're just looking at the graph and interpreting. Okay, and all of these things are pretty, hopefully for you, pretty easy to tell just from looking at the graph. You just need to make sure that you're paying close attention to the unit that we are increasing by on both axes. Otherwise, it's just kind of pulling that important information out of the graph.